Good afternoon, everyone. So this is Prashant Ayan from Altair India Bangalore office, and I welcome you all for SAE India SUPRA 2005 online training session day 5. And I'm excited to see like so many of you have shown interest in this particular topic, and I assure you like this will be a very exciting topic because here we are dealing with a lot of dynamic stuff. So to start with, so here our objective by the end of this training session is to understand how to do a dynamic simulation on the impact attenuator. So I'll be showing the demo on that one, how to set up that and how to run the simulation. But before that, I felt it is worth to understand regarding the tools what we are going to use and what are the different problems which you can solve, including this, yes, of course, apart from this also. So I have some short presentation which have these details. So I'll quickly finish that and then I'll move to the actual demo part. So I hope my voice is audible for all of you. And since there are like a lot of attendees, so it will be difficult to take the questions. So of course you can raise the questions. So we will record that and we'll answer that. Maybe either during the session or for sure. Like we'll take that queries and we'll reply maybe the email. So please do ask questions. Okay. So here I'm trying to give you a brief about the different tools Altair has. And you also have to use some of the tools for this application. So that's why I'm showing you these tools. So if you have to perform any CAE simulation, basically you'll be requiring the tools in 3 areas. Like one is pre-processing, where you will build the model, build the FE model, and you require a solver. Solver is a ghost, and you require the aids to fire the job into the solver, and you require the post processor to see the results. So in Altair, there are different preprocessors for different applications. So the major one being the hypermesh, which most of you may be aware, and we have a specific preprocessor for the crash setup also, which will just make your life easy for the crash setup. But everything can be done in the hypermesh itself, and that is what we'll be doing it today. And for manufacturing application, we have Hyperform, and for the MBD we have Motion View, and for CFD we have Aki Control. There are different preprocessors. And for the post processing, we have Hyperview and HyperPath. So also the intention of showing these solvers is like for any CA engineer, the graduation is first you may start with the model building. That is anyway the first step. So every CA engineer should know that. And then you may start doing the static analysis. Thereby you understand the linear part of it. And then you may add little nonlinearity into your domain. You may do some nonlinear implicit stuff. And then the cream area comes, which is the nonlinear explicit, which are like large strain, large deformation problems. And today what we are talking is this nonlinear explicit case. So the impact attenuator case which we'll be solving, that will be solving it in a nonlinear explicit solver, which is Radioss here. So like at the student age, because of your time limitation or because of the other pressure, you may be jumping into this explicit simulation directly. But what I suggest is you have to come to a your basis will be good if you have the proper understanding regarding the linear, the implicit, nonlinear, and then if you jump into explicit. So as I mentioned, like explicit is one of the cream domain in this analysis world. Okay. So I'm not getting into other tools. So my idea here was to show you like how you have to make your career plan in the CAE starting from here. Okay, so to build any crash and impact problem, so there is the flow process. So first you may do with the component level meshing, and then you will first you will do the component level meshing, and then you will set up the model. You will run the simulation. Sometimes you to run the simulation, like you may be requiring some data from the manufacturing, and sometimes you require tools like you require the human models, you require the barriers, energy absorbing barriers. So you may be requiring sometimes these tools, and when you run the analysis, like you'll see the results, and if required, you will do the optimization. So these are typical flow of any crash and impact simulation. So if I have to map the tools, how you will be doing this. So model building, you may be doing it in Hypermesh, and setup, you can do it in both Hypermesh and Hypercrash, as I told. You can solve the job in Radioss, and you can see the results in Hyperview and Hypergraph. And if required, if you want to impart the manufacturing effects into your model, you can do the manufacturing simulation, bring the results of that, and use that also in the crash. And if you require human models, so those are also available with us. And of course, optimization. So Altair is the only company which has all the tools which is required for this crash and impact simulation. Okay. And now something to take pride about. So these are the first 5 cores which got 5-star rating way back in 2000, 2007. And these are the first 3 vehicles which got 5-star Euro NCAP ratings way back in 2000. So now it is most common, but this is way back in 2000. And the insurance rating, the IHS rating, car awardees, so these are the like top performers in that category. So why I'm showing this? So what is common in all this is all of these vehicles are engineered using Radioss. So that shows the power of the Radioss and how customers are using this, how the auto OEMs are using this in day in, day out. Okay. Okay, so it is not, when I say Radioss, so now also like I started with my discussion with the automotive, and I showed a lot of the automotive stuff also. So does it mean like Radioss has solution only to the automotive? No. So wherever you have these large strain, large deformation cases, the explicit cases, so that is a case for the Radioss. Here I have taken some of them. So of course, again, this is still in automotive. So this we put it in the safety domain, where you have the interactions between the dummy, airbag, seat belt. So we study the safety simulation part. And there will be some, there are cases like FSI simulation, which is fluid structure interaction simulation. A simple case in the automotive is we have the fuel tank sloshing simulation. So where you are studying the hydrodynamic pressure which is applied on the walls of the tank. So there are many FSI cases like that. And the extreme explicit case, which is blast, you can do that in the Radioss. So we do the blast simulation using Radioss. So here I'm doing a blast and seeing the shockwave propagation, and I'm seeing what is happening to the structure. So this you can consider one of the very extreme nonlinear case. And one more like a FSI kind of case where I'm seeing the splashing effect. So where I have the particles and we are seeing the splashing effect. So some of the very advanced rupture models, like rupture mechanism, like we have the XFEM method to represent the exact rupture physics. So that is using XFEM. And in the biomedical field, people also study the injuries. Because there are human models which are available, so people also do the injury study. So these are some areas to talk about. There are like thousands of different areas where you will face the extreme nonlinear events, and all those areas you can use Radioss. Okay, so to briefly categorize, like these are in terms of say the business verticals, so to say. So these are the different solutions what Radioss can provide in different areas. So now what we are talking about, it falls mainly under either this or this. There is not much of difference between these two in terms of at least the setup and the way we do the activity. So like our discussion will revolve around these domains. Okay, so now the case what you are going to solve, it is very similar to like you also might have done the Google, and you might know that this is a standard automotive case. In the Indian context, so we do the impact with the rigid barrier and rigid flat barrier. So here the video what I'm showing is a deformable offset barrier. So we are doing a impact with it. So in this case the barrier is deformable, and we are doing the impact with the car. And in the case what we have in hand, where we are fixing a type of deformable material to the vehicle, and we are doing the impact with the rigid barrier. Okay, so this is a standard automotive case which we do day in, day out. Okay, so now with that brief, I am coming to the actual case. So we have to perform this dynamic load simulation on the impact attenuator. So that is the intention. So if I look at the problem looks like this. So you have a geometry which you have to come out with. So here I have taken the geometry which is directly available in the ICA website. So I have taken the geometry, and the criteria is so this impact attenuator, which also in the background represents the mass of your complete vehicle, which is around 300 kgs, will impact with a rigid impactor at a speed of 7 meters per second. So this is the problem statement. Now, when I was when I was doing some research on like how actually maybe your previous in the previous year, like how actually are doing this testing and all that. So I came to know like most of you people are taking only this part with this attachment, and some are doing with the drop test, and some may be doing the actual impact. So, but I didn't heard of any case where you are doing the test with the full vehicle, like whatever the vehicle which you are building. So I don't think in terms of testing, you are not taking, I have not heard of any case where you are taking the full vehicle and doing the test. So even in the setup case also I have taken just this impact attenuator. I have not considered the full vehicle. But if you ask me like, so this will of course satisfy the requirement what you are looking for, but from the physics point of view, in the entire vehicle, the damages which will come on the vehicle will be entirely different when we see it at the full vehicle level. But here the objective is also very clear. Like here the objective is just to see the total energy absorbed by this impact attenuator when the impact happens, and also see the G levels. So that can be completely done using the standalone impact attenuator. So no need to go for full vehicle. That is true in terms of the regulations or the specification what you have it is concerned. Yes, it is true. Okay, now with this I will jump to the actual model setup. Okay, fine. So I'll be using HyperMesh to do this setup completely. So I'm launching HyperMesh. I hope you all can see my HyperMesh window which has just opened. Okay, so in the when you launch HyperMesh, it will ask you to select. So HyperMesh being a neutral preprocessor, like HyperMesh can be used to prepare deck for many different solvers. So you have to select the solver which you are going to use. So in this case it is Radioss, and when you drop down you will see different names. So they are basically different versions, the older versions. So I will do my setup with the latest version, which is block 120. So I'm selected block on 20 and I'll say OK. Okay, so now I have launched the hypermesh. Okay, now I'm importing one file. Okay, so this is a blank file actually, but it has just one curve. So it has one curve data. Okay, so it has some curve data, and basically I'll be using this curve information in the material. So like instead of typing all these things, I had just created on one blank file with only curve data, so that I'm starting with that one. So this curve I'll be using it later. Like at that moment I don't want to keep typing many rows and columns, so I just bought the curve upfront. Okay, so the first step is to bring the geometry. So I will import. So there are many import options. I have to import the geometry. So I'll go to this tab and I will browse the geometry. I will import it. Okay, so you have the geometry. Okay, but I will not be using this exact same geometry. The reason being, when you see the result, you will understand like this geometry, like this object will get into extreme deformation, extreme permanent deformation. So then, like, if I go with this geometry, and then my meshing will be of course difficult, and my elements may not be so good. So those bad elements, if they go for extreme deformation, it is very difficult to handle. So I don't want to get into that situation. So I am using a simplified geometry. Here, import. Okay, so if you see this geometry, yeah, so I have just taken the outer boundaries of the geometry, like the original geometry. And here, for me, these maybe the fillets and other things, it will not matter. It will definitely not matter in my analysis, because if you see at the end the extent of deformation what it undergoes, in that context, like this will not matter me much. And also because of the analysis challenges, I cannot go with these geometries. So I'm not considering that. I'm considering, you can say, a outer box of the original geometry. So I have just taken the outer box of it. And also it will simplify my case in this type of demo where I have to build the model very quick. If you can if you are in the original geometry, if you can still do a very good mesh, you can of course use that. Otherwise you have to use something like this. Okay, now I don't require the old one, so I'll just delete that, because from now on all my work will be on this geometry. Okay, so now I have to start doing the meshing. So for which I'll create a collector, some name shell, and I will use a card image which has to be part. Click on part, and as of now there is no property, so I have to create the property for this. I will say create property, shell, surface, card image, V1 shell, thickness I'll specify 5. I will go inside the card and I will change number of integration points to 5. Okay. As of now, I am not explaining you any of the solver concepts. there is a lot of theory between each of these cards, when to use that and all that. So I'm not getting into that theory. So my discussion is at this moment it is particular to this case, because in 2 hours that is the best what we can achieve. Okay, I have created the property now, and I will create a steel material as of now, but this is not of steel material, but at this moment allow me to create a steel material. Okay, I'll create an elastoplastic material, the most widely used or most easiest, Johnson Cook, created it, and I'm entering the steel parameters. One thing what you have to take care in the analysis is you have to maintain the consistent unit system. Solver will not understand the unit systems. So the unit system what I will be following is Newton, millimeter, tons and seconds. So I'll repeat it again. So the unit system what I'll be following is Newton, millimeter, tons and seconds. So thereby my stress will be in MPAs. And here in that regard my density for steel is 7.89 e power minus 9 tons per mm cube. Okay, and Young's modulus 2.1 e power 5 and Poisson's ratio 0.3. So this is yield stress. I will assume a yield stress of 250 MPa, a hardening parameter of 300, hardening exponent of 0.2, okay, and ultimate stress of 450. Okay, so these hardening parameter and hardening exponent will define the slope. Okay, I have created the material now. Okay, so now my shell is complete. My shell is having a property and material. So for every part what you create, so it should have a property and material, except rigids. Okay, for rigid it is not a part, no material, no property, but for all your shell and solid it should have it. Okay. Now since I'm in the process of creating the properties and creating the components, I will create the component for the foam also. So basically this is a foam material which is a crushable foam, something like a EPS material I would say. So for which I have to use a particular material now. So upfront I will create both property and material for this. So let me create that. So I will create it for foam. Okay, so card image again it is part, but property is not shell anymore because I'll be doing this solid meshing for that. So I will say create property, okay, foam. It has taken the same name as my, it has taken the same name as my part, and type is volume because it will be a solid mesh, so it is volume, and card image is P14 solid. So in solid, of course, like the geometry itself will define will represent everything. You don't have to define any thickness or any other stuff. So I will create return. So as of now, I have created the property for the foam. So now I have to create the material. Foam, create material. So this is a EPS material which is, just a minute. Okay, this is a foam class. So which is we have 33. So I'll be using this material here, created it. So this material requires density. So I will use a density of 6 e power minus 10, and I'll use a Young's modulus of 15, very low. And here the important thing is that function. Okay. So I have to input the function for this. So which is a this function will represent, it is a stress versus volumetric strain. So I have to input the stress versus volumetric strain function here. So okay, I have the function tab here, so I'll click that. And so if you remember, like earlier I mentioned about one curve which I brought it along with the material. So I'm just calling that function here. So this is a simple law with which density, Young's modulus, and this function is important. So this function is a function between stress and volumetric strain. So for the kind of material what you are using, so you have to get these parameters. So because this is the very important one, which will define the behavior of the foam. Okay, so now I am done with the component for foam also. Okay, so now I have oh, I think I did a mistake. Okay, so I didn't created the initial. I entered everything. I think I forgot to enter the. I forgot to create it. Okay, that is very quick now. Create. Okay. So now if I see, like, I have the original geometry, and this is this collector, I have the foam, and I have the shell. So I have all those parameters. Now I'll start the meshing activity. So global size I'm maintaining 10 here. Okay, so I'll mesh it with a global size of 10. So I want the mesh to come in current collector. I want the mesh to come in the current collector, so it is here. I will say mesh. Just remember these densities because I want the same density to come at the other end. So it is 11, 11, 21, 21. Okay, return. So here also I will do the same mesh. Okay. So I want to achieve the same because I want to use a particular type of solid meshing for which asks for same elements here and there. Okay, done. Okay, so now you have shell at both the ends. Now I will use 3D linear solid. This is the very basic option of creating a solid mesh. Basic, very easiest one. Okay, I will say element by face, and I have to select the alignment and element by face, the alignment. Okay, and I have to tell, like, in this path I require how many rows of solid. So I have measured it and I feel 15 rows would be comfortable. So before creating, you have to change the current collector. Otherwise your solid mesh also will come in the shell collector, which is not correct. So I will change the collector to foam. Okay, and I will say solids. Okay, it is telling the number of elements in each group, they are not equals. It means I have done some mistake while doing the edge edit. Means while correcting the number of elements in both the things. So I have to again check that. Yeah, so edge. So here it is 21. Okay, now it is 21, 21, and I'll make it 11 here and here, and match. Return. Okay, now it looks okay. I'll come to linear solid again. Element by face. Element by face. And for this, I will select the orientation this, and for this, the same elements you have to select, because the growth will happen from here to here. So you have to select the alignment same here and here. Okay, and now whatever the solid will come, that will come in this collector. I will say solid. Okay, so now you have solid elements in these locations. Okay, so after the creation of solid, actually you don't require this shell element. So display. Now I will delete these shell elements. Okay, but I will retain this phase because now I don't want to create a direct impact with the foam. So I want it to tie this, or I want to lock this to a structural member, and then I want to do the impact. So for that purpose, I will offset this shell. So for that, I will go to Tools, Translate. I will select all these elements. I will say duplicate original component, because if I translate the same shell elements, those shell elements are already attached to the solid. So if I translate that, it will pull my solid also. So I don't want that to happen. So I want a separate shell elements. Okay, now I have duplicated. Now in the Z direction, let's say I will move it by 5 mm in negative Z direction. That's why I will say translate minus. Okay, so now you can see that it has created one mode here. Okay, so now I don't require this. I don't require these elements. Please delete. Okay, so now we have solid elements and we have shell elements. Fine. And at this stage, I will check my component table just to confirm that all my parts has both property and material. So many times we create it and we forget to assign. So it is better to see this component table to confirm that whatever part I created that is having the properties, they are having materials, and shell is having thickness. So this confirms that data is complete. Okay. Now just to make it little bit good looking, so to say, I want this steel plate to be little bit wider compared to this solid. So let me do some geometric operation and make it bigger. So I have removed that geometry, say none. Okay, now I have this. In every direction, I just want to increase it by say 10 mm. I will measure how much it is. So I will measure, it is okay. in every direction I wish to move it by say 15 mm. So I'll again go to Tools, Translate. I will select the nodes in this phase, and in X direction I will move it by 15 mm, 15 minus, then same in this direction, plus, same in this direction. Now in Y, 15 positive, and here 15 negative. Okay. So it's looking good now. Fine. Now my next work is creating or gluing this object to this one. So there are various different types of connections which are possible, like the simple connections may be rigid elements, like putting the connection elements, 1D rigids between these two. But if you do that, you have to do that at the selective location. Now let's say like I will do that only at this core location. Then you have to create a sliding contact between these two. Of course we can do that. That's not a problem. But that will like add to further steps and may make this model a little bit complicated for you. So I don't want to do that now. So instead of that, I will use a different type of connection which is very simple. So for that I have a contact. That contact will tell like this shell is tied or glued to these solids. So to do that, I will go to Analysis. Yeah, sorry. So before going that, I have to create a entity set which I'll be using it later. So I will go to Entity Set and I will create a node set. Okay, so I have to select the nodes. Nodes by phase. So these nodes I want to tie. So let me create it. Okay, I have created an entity set. So that I will use it at a later stage when I am creating the tied contact. I am doing this with the assumption like you have little exposure with the hypermesh. So that is the reason like maybe some of my actions may be fast for you because I am doing with the assumption like you have little exposure to the hypermesh. Okay. So now it is creating the tied contact. So I will go to interface. I will say tied. You have to be in create. So I will say tied. The type is type 2 now. Type 2. And you have to say create. Add. I have to say which is master. For selecting master, there are different options. I will go with component. I'll click on component and I'll say update. And for slave, I have already created a set. So that set I'll be calling it here. So sets, node, select, update, and review. So when you do the review, it should look like this. So it should look slave in red and master in blue. So then what you have created is correct. It has come properly. Okay. So now one activity is over. So wherein like you have tied these two. Now you require the rigid impactor. So as the regulation says, like this should travel and hit against a wall, non-deforming, non-yielding wall. You have to create that. So in Radioss terminology, we call that as a rigid wall. So you can create a rigid wall. So for that, I will select a approximate center node, which I require a reference. That's why I'm doing that. So I'll go to again tools, translate. So for me, let's say approximately maybe this may be center node. Fine. I will say duplicate 2 times. There is a reason behind that. I will say nodes duplicate. I will again say node duplicate, and I will make it to travel in Z direction, say by 10 mm. Translate. Okay. So why I did duplicate twice? Because I also wanted to see this node. If I say duplicate only once, then just one node will come and sit here, but it will not show this node. But I need that for a particular purpose. That's why I said duplicate 2 times. Okay. So I have a node here. Now the intention is to create a wall at this location. See, ideally in the simulation, now let's say in the setup, your object is quite far and you're creating a wall somewhere at a distance. You are making it to travel and impact. So this is how we do the testing. Or even when we are doing it like a drop test, so we will calculate the height. Like if you take the object at what height, then like if you create a potential energy and how that will get converted into kinetic energy, and you will achieve that particular kinetic energy, or you will achieve that particular total energy in this case. So we'll calculate all that and we move the object to at a certain distance. We keep it at a certain distance. But in the context of analysis, we don't do it like that. In the analysis, like if you're keeping it that much far, then that the time what it takes to travel from there to here, it will be a very big time. And in that time, it is not giving you any, like there is no change in the result. So it is not good to keep your impactor at such a far distance. So here what I'm doing is I'm keeping the impactor very near, at a distance of 10 mm. Even that much is also not required, but I just want to show you the impact. That's why I'm keeping it at a distance of 10 mm. Okay, fine. Now I had to create a wall. So for creating the wall, I'll go to analysis, rigid wall. I'll click on create and I'll give some name. This size is immaterial because what I'll be creating is an infinite rigid wall. So this size will only show you for representation. Let me take 100. But this size is immaterial because what I'll be creating is a infinite wall. Okay. So I will say create here, create, and then I'll come to, then you have to come to geometry. And here I will use this node. So base node is the location where the rigid wall will come. Okay. And now I have to say that from which direction you are getting an impact. Otherwise this rigid wall will not understand. So for that purpose, see like here the shape is infinite. There are different shapes are also possible. Okay, but my requirement as of now it is infinite plane. Now, okay. Now this is your base node. I'm telling like impact is coming from, so your first node N1 should be this and N2 should be this. Okay, so update. I have created a rigid wall. What you should ensure is, see there is one arrow which it is showing. So it should be in the direction opposing your impact direction. Then only this R-wall is going to work. Otherwise the R-wall will work in the other direction, not in this direction. So if you want this foam to impact here and stop, then the normal what you are seeing, it should be in the direction opposing the impact. So now what I got is perfect, it's correct. Okay, so now I have created a wall, but for this wall I have to tell that what you have to stop. Otherwise this wall will not understand like what it has to stop. So for that purpose I am telling, now I will go to add and I will tell like you have to stop all these nodes from crossing this.
Now you can see the questions. The number of attendees.
Okay, I'll pick this, you can select add, update, review. So even here also when you do the review, you should see something like this. Okay, your R wall in blue and your nodes in red. So then the R wall creation is correct. Perfect. Okay, so this is done now. So now these things are disturbing my the way I look at the model, so I just want to switch off them. So I will say hide. So they are there. I just hide it so that they don't disturb me. Okay. So now you have created. So till now you have done the meshing and you have assigned the material and property for this, and you have created the wall on which the impact will happen. And since these two are separate component, you have created a tied connection between these two. Now some of the last step, what is our last but one step, which is what is remaining, is I have not applied the load. I have to apply the velocity. That I have not applied. I have to apply that. Now before that, I want to make this plate as a rigid. So for that, I'll create one more collector, rigid. So a collector for rigid should essentially be no card image, no property, no material. So this is very important. So the collector what I create for rigid, it should be no card image, no property, no material. I will create that, return. Now come to 1D, widgets, create. When you open this create, it will look like this, but you should change it to multiple nodes and calculated nodes. So when you are creating a rigid, the option should look something like this, multiple nodes, calculated nodes. Now I will select all these nodes and make one rigid. So I will say nodes by collector, select, create. I created a rigid here now. Okay, and on this I'll be applying my velocity. So I created a rigid here. I'll come back. Okay, so now the job is to apply the loads. So for that you have a very good option. I will go to utility. I will go to BC manager, which is boundary condition manager, and I will enter the name, velocity, and the type of load is initial velocity. Okay, so this is a impact case. So your load has to be initial velocity. You can see the other type of velocities here, but they are not your loads. So when your case is impact, it has to be initial velocity. And I have to say like on which node I have to apply this. So I will select this node here. Okay. Proceed. So since I have applied a rigid body here, the velocity what I am going to apply here, the same velocity will be applied on this entire plate. And since this is tied with this, so this will also get the same velocity. Okay, now I have to apply the velocity in a Z direction here. I have to apply VZ. So the velocity is 7 meters per second. And as I mentioned, my unit system is in a millimeter. So I have to apply 7,000. Okay. That is because my unit system is like that. So it is 7,000 millimeter per second. And I will say create. Okay. So now you have the initial velocity. Clear. Okay. So this model is almost setting is done. Now the final steps, like I want results now, because if you set up the model and if you run it without asking the particular results, then your run is waste. So for that purpose, I will go to analysis, output block, and I will create request. Like first it is parts, and for that you have to bring it as components, and I'll select these two components, because when I show you the energy absorbed by the part, so then while doing that I have to see the energy on this part, so I have to request the output for that. So I'll click on components and I will select these two parts. You don't select the rigid, only these two are enough. Select, you have to say create, and you have to say edit, and in the variable you have to define DEF in capitals, in capital letters. It means like whatever the default output which should come for a part, so please output that. So it is def, okay. Now the other output, say node, and here I'll make the selection as node, and I'll pick this node, because from the node I'll get a displacement, and then that displacement I will do a double differentiation to get the acceleration. So for that purpose I have to request output for this node. So on that node it will give me displacement versus time graph. Same procedure, I have picked the node, create, edit, and DEF, return. Okay. If I am interested in when the impact happens, what is the force which is coming on that R wall, then I have to create one more output request. I'll give some name and I'll go to groups. In the groups, I will pick up that group which I created. Select, create, edit. Okay. See, sometimes this issue happens when you're not able to enter in this variable. It happens sometimes. So then you have to just change this number from variable 1 to 2, then it opens up, then again make it as 1. Some workaround. Sometimes it gets a little angry with you. Okay, so again def. So I'll define the variable def. Okay, so now what are the output requests I created? So I created for parts, I created for node. On the part I'll get the energies, on the node I'll get the displacement, on R wall I'll get the forces. So all these output requests I have created. Fine. Now in the explicit analysis, being this a time domain analysis, whereas all your static or implicit nonlinear, they are not the time domain analysis, whereas this is a purely time domain analysis. So you have to specify many of the entities with respect to the time, like the first one being how long you have to run this simulation. So that you have to specify. how long, when I say it is not your clock time, it is not the time what you are seeing in the clock. It is when the impact is happening, how long I have to capture that process. So now I have given the velocity, so it will do the impact. So this comes by experience, or when you do 2-3 cases, when you and then you understand like how much time it will take to do that impact. And by the when I run it, I will also show you how to judge that one. Now to put all those values, you have to go to this control cards. Control cards. In this, you have to enter majorly the 4 fields. So be careful with that. So I will show you the fields. So you have to go for engine run first. So I will go for engine run. Engine run. So here I have to specify the end time. So I will run it for 100 milliseconds. So 1/10 of a second. See, any explicit analysis, we run it for, like, we assume that event is happening very fast. Our explicit analysis is applicable for only those events which are happening very fast. So if you take a front impact of a car, it happens nearly in 120 milliseconds. If you take the drop test of a mobile phone, which may happen in a span of say 10 milliseconds. So these are like very fast events. So I feel like this model, if I run it for say 100 milliseconds or 0.1 second, that is enough. Okay, that is what I specified here. I'm back. Now I mentioned like 4 important parameters. Now the next important parameter is at what frequency I want the results. Now it is going to run for 100 milliseconds. So it would be nice if you have animation at regular intervals. Otherwise, like, you have one animation at the beginning and one animation at the end. So that is not nice. So we want to understand like what is happening progressively. So for that purpose, there is a card which is anim dt. So it is in alphabetical. So I'm just jumping to anim dt. So we have anim noda here, previous anim dt. So here I specify the frequency. So since I'm running for 100 milliseconds, let me extract the animation at every 2 milliseconds, which will generate 50 files. So I'm extracting the animation at every 2 milliseconds and I'm running it for 100 milliseconds. So it will generate 50 files. Okay, so this is the second important parameter. Now the third one. I will be getting many information in terms of graph, in terms of plot. But I have to tell the solver at what frequency you have to capture the data for that graph. This is important. Okay. Otherwise, it will not capture the data what is required for the graph. I will go next. So that comes in the engine T file. Engine T file. And normally I will select this frequency more finer than my animation frequency. In the animation, if you remember, I selected 2 e power minus 3. Here I will select 2 e power minus 4. Okay, 10 times less than that, because I want my graph to be more final, not coarser. Okay, so now 3 important entities are over. Only last one is left, which is type of result. See, by default, it will give only displacement. But if you want other type of results, like a distress and strain, then you have to explicitly ask for that one. Otherwise, it will not output. So for that, I'll go engine anim element, engine anim element, and I will say I want element plastic strain and I want von Mises. one message. So I will tick those two things. Okay. Okay, so one card I think which I forget to told was previous. Okay, so there is something called solid default, in which I strain you have to make it 1 to output the result for solids. So this you have to make. So these are some of the control cards which I activated. Okay, so now you are done. You are done with the setting up. You have requested the output. So just if I have to repeat the process again, then I bought the CAD model and I did the meshing. So for that, since I had to do the solid meshing, first I did the shell meshing. Then using linear solid, I created solids. Then I created the materials. I created the properties. So using that, I created the collectors. And I, like between two parts, I created the connections. I created a wall and I applied initial velocity, and I requested some of the outputs and I added some of the control cards. So this process, like it may be like if you see this, it may be a 10-step process, but this is the same process which is repetitive like if you do any other case also. So this process remains same. For any impact analysis, this process remains same. So maybe your components will increase, your materials will change, your connections may change, but this process will remain same. Okay, now I'll come to model here just to understand what all I created. So if I remember, like when I bought this model here, you are having this curve which I bought from outside and maybe some components. So now you have many other things which got created here. Okay, now it is time to export. So I'll go to export. I will make a folder. _1, save it, and look at these options. So it should be something like this one only. So now I have created some of the entities in the control cards, so that will go to the engine file. But if I don't tick this, those control cards will not go. Then you cannot run the job. So that is important. So it is getting into, so you have to tick this one. And always it is better to keep the export option as all. Sometimes it will look like custom. Don't keep it like that. Always keep it as all. Okay, so with that I'll say export. Okay, now I'll go to that location. Oh, you can see two files here. So it is always a good idea to open the file and see what it contains. So it is containing the material what you have created, do both the materials, nodes, which is the next keyword, brick elements, shell elements, shell property, which is having 5 mm thickness, solid property, a function which is used for material, which I'm using it for material. So I'm applying a load which is initial velocity. So I have created a contact which is for tying two entities, which is this inter type 2. I have created a OR wall, which is the wall on which the impact will happen. So it is created by using some sets. So these are two parts. So two part is having a material ID and a property ID, material ID and a property ID. And I have requested output for a node, output for a part, output for a contact. So what is learning a solver means? If you are able to read this file, it means you know the solver. So it is as simple as that. So don't like blindly create the file in the hypermesh and try to run it. It is fun to see this text file and correlate the parameters with your understanding, because when you face the run issues, you will appreciate of coming here, reading this, changing the parameters, and it's quite fast also if you want to change some of the parameters. So it is always a good practice to read these things. Okay, now my file is ready. Now I want to fire the Radioss job. So for which I'll go to Start menu, and we have something called Radioss Manager. So as for me, I have kept it the shortcut here. My shortcut is here, which your icon will look like this, Radioss Manager. Click on that and browse the 40s.rad file. 40s.rad. So this is called starter, this is called engine. You have to browse the 40s.rad file, open. These options are there for different purposes, but for you and your models are small, so don't use any of these options. Okay, so you can just say run. I'm hoping I will not get any error. Oh, I got an error. Okay, so this error is in the TH group. So I have to see the error in this. Okay, so it is telling some issue with my TH for R wall. So I'll just try to check that. Okay, so here the mistake what I did is, see, every time when I was creating the variable, I had to enter it as DEF, as I told you. So here if you see, oh, I have DEF. Okay, so let me recreate this. I'm deleting that group. So I'm deleting that output request here. Yes. Okay, so let me recreate. Okay, groups, create. So groups, I will select this, select, create, edit. So the mistake was here, when you go with rwall, here your keyword has to be rwall. So it is not inter. So that was the mistake. So I will change it to rwall, because if you see here, we have multiple options here. So a group can be a contact, a group can be a rwall, it can be a section also. So I had to explicitly say that this is a rwall. So that's why if you see my deck also, here it will write it as th inter, whereas it is rwall. So that's why it was not okay for that. So now I have changed it, and I have to write the DEF. I have to write the DEF. Fine. Export. Same file name. Export. Yes. Okay. So let me fire again. And run. Okay. So with that one error, like I corrected that error, now it is running, and it is also telling the remaining time is around say 39 seconds, and it is changing because the time steps are changing. So we have to wait for some time till it completes. You can also check the intermediate results. Once you have 2-3 animation files, you can check the results. But I want to wait, since it is taking very less time, I just want to wait and see the results once the run completes. Okay, so that is the estimated remaining time. Sometimes it increases and decreases depending on, we have a concept called time step. So if solver is struggling at some region, the time will increase. So again, when it is comfortable, time will reduce. Okay, so we're almost at the end. Okay, so the run got completed and we have the results. I'll click on results here. Okay, so I have the impactor. So I'll just keep it in proper orientation. With the mesh on. And now you're seeing the impact and it is trying to compress. Okay. Fine. Now the next okay. This impact is not severe for me because I have not accounted one of the major aspects which is there in the regulation, which is like I have to apply a mass of 300 kgs, but here in nowhere I mentioned like I have the mass of 300 kgs, correct? So that's why this severity is very less. Okay, but my run is going on, so that is a good sign. So your setup is correct, everything is correct, except that the mass of this is not 300 kgs. So now to update that, I'll come to my model and I have option here. I'll go to card edit. I'll click on this green element carefully and I'll say edit, and here you have a mass. Here I'll specify 0.3 tons, which is equal to 300 kgs. Okay, 0.3 tons. Return, and let's export it to a new folder. export. Okay, so now I have a new folder with the files, and I will fire this run. Okay, so run. So I'm just checking the inside file. Now I have 0.3, which was not there earlier. Okay, so time step is dropping, so your runtime is increasing, which will continue for some time, and then again it will come to a proper one. Yeah, so now it is reducing again. So approximately another 1 minute, so it will take for run. So we have the options to speed up the run. We can use multiple cores and other stuff, but I'm not doing any of that here. I'm keeping it very plain and simple. Explicit run can be highly scalable by using more number of cores, more number of CPUs. And it is worth, you have to do that for the bigger models. But this model being very small, I don't want to do, I don't want to use all those options. So here I'm just running with one CPU, one core. So if you see here, it is I didn't select a number of 4 here. Did I select it? Oh, this RAM okay. This RAM I'm running with 4. Okay. So while running it the first time, I removed this option. I was not using that. But anyway, now I have. When I opened the window, it was already there, so it has taken the 4 cores. Okay, so it has almost come to an end. Okay. So you have to give little time till it shows this result. Okay, I'll keep it in a view. Shows on the mesh and impact. So now it looks scary. Yeah, so this is the kind of the large deformation you can you'll be able to solve when you use the nonlinear solvers. Okay, so now this is what I was expecting. So everything is effectively working here. Your wall is working perfectly, and my materials are good. The load is perfect. I can even take the section, which will be nice to see. So let me take the section in extraction. Okay. So you can see like how it is getting compressed, the elements. Yeah. Okay. Now, like this will not tell you what you want. Like this will only tell you like, okay, it is telling you the behavior that is looking fine, that is looking perfect. Things are like the foam is getting compressed, but this is not telling you any numerical value what you are looking for. So let's come to that numerical aspects. Now, the first thing before getting into numerical, I will open hypergraph here. I'll split the window into two, and here I'll open hypergraph. So now I'm doing post processing. So in the hypermesh, I did all the pre-processing, and I fired my job using Radioss manager, solving the ghost which is working in the background. It is solving the solution for you. It will give you the files, result files, which you can view it using hyperview and hypergraph. So in the hyperview, to pull the files, you have to pull them as .h3ds. In the both model and result, you have to pull them as .h3ds. It will come there. And to see the plot, click on this, call T0. Okay, this is not the file. New run to call T01 time history file. So call that. Okay. Now, if you do any impact analysis, the first thing what everyone expects from you is to show the energy balance. So you have to, this should be one of the important parameter in your results. So for that, I'll select global variables, click internal energy, kinetic energy, contact, hour lash, and total. Click on magnitude, and so while selecting these intermediate things, I was holding the control and I was selecting these things. Click on magnitude and click on apply. See, this is the beautiful energy balance graph which everyone expects. Okay, so here if you see, like you have to compare the start of this kinetic energy value with your mass and velocity. So you know kinetic energy is half mv square. So you multiply with your mass, which is 300 kgs here, and the velocity 7,000 millimeter per second. So if you multiply those things with the kinetic energy equation, it should match with this value. So initially it was like moving for some distance. Then once the impact happened, there was a sudden drop in the velocity. So there is a sudden drop in the kinetic energy. So you can see both the things in sync to understand this graph. Now I just delete this section, which I don't want now. Okay. Okay. So now I'll move the animation slowly so that you can see. Now the compression is happening. So the compression is still happening. So by the time it reaches here, that will be the end of the compression event. Yeah, so that is the end. And after that, it is a bounce back. So when it bounces back, it is bouncing back with one constant velocity. Mass is same, but the velocity got reduced, so it is coming with one constant velocity. So by seeing this, what it looks to me is it is enough to run for only say 50 milliseconds, because once the energy is balanced out, there is no need of running for a long duration. So even if I even in the time what I was entering here, analysis, control cards, in the run, instead of 0.1, I can even put 0.05. That will be my end time. But you will not know that unless you run it one time. Okay, so now, so this is what the energy it is observing. Now, here, anyway, the other parts are rigid. So I will plot the next set of energies now. Let me make it as 3 parts. Okay, here also I'll bring one more hypergraph window. Now, again, I'll pull the same T0 file here. Okay, so we are interested in part-wise energy. So I click on part, this foam, internal energy, apply. So this is getting into that nearly say 7.4 joules, what you expect it to absorb. So it is absorbing that much of energy as per the objective of this problem. So that is a good sign. And here if you see, the internal energy of this part is also equal to the global energy. That is why, because apart from this there are no other parts which are deformable. That's why it is happening like something like this. If you make your problem little bit detailed, if you add some more parts and all that, then you may see some difference between your global energy and the energy absorbed by this impact. But what we are interested here is, of course, energy absorbed by impact attenuator. So the first objective is met. So it is absorbing this much of energy, which is a good sign, and that is what we want. Now I'll add one more graph. If you are feeling it, okay, too much of graphs here, let me take a new page. I'll take a new page, page 2 of 2. In this, I will show you the other entities. So what is the force which is coming on this R wall? So when the impact happens, what is that force which is coming on it? It is not your, like, it is not the objective of the problem, but still I want to check it. Say apply. So this is, this much of Newton is coming when impact happens. Okay, so this is one of the information which you are getting, and you are getting this information because you have put the R wall in the output block. So if you remember, like, I'll again go back. I did something here, analysis output block. I created this, and also I did one mistake also while doing this. So I created this, that's why you're getting this result. Otherwise, you will not get it. If you don't do all those things, you will get only this global variable, not any of this. Okay, now this is one information where it is telling at the impact, this was the kind of force which came on the impactor. See, this information will also help if you are designing this. See, now in the for me, in the simulation, it is very easy to create a rigid wall, something like this. Sure. Okay. So in the analysis, it is very easy for me to create a rigid wall, something like this. But if you are doing a like a physical test, and if you are asking someone to make this rigid impactor for you, then this post data may be the data what will help you to say them, like, the rigid impactor what you design should hold this much of force. So by that, at least you can design a proper impactor. Okay. Now the next data, which is one of the objective, to see the G levels. So for that, I'll take the node. So this is the node which is there on the back of that. This is the, like, I have selected a node here. So that node is this node. I also have a method of reading the acceleration directly. So I have the accelerometers. I can use that and directly read the acceleration. But I don't want again to complicate, and I want to show you the easiest method. So here, what I'm doing is I have selected a node, and on the node I had to plot Z displacement. So dz, apply. So this is the displacement. Now we know, like, if I double differentiate the displacement, I'll get the acceleration. So if I do single, so this is displacement versus time. So if I do single, it is velocity. If I do double, then it is acceleration. So, but how to do that? Now I have a curve here. So just click on the curve here, right click, math operations, do double derivative. I did double derivative. It came something like this. You can read this value directly, but if you don't like it in this way, I will just offset it. Because this is a like retardation, it is showing it in a negative. I will just change the sign for you. I'll make it minus. Apply. So now you have the G. So now how you have to read this value is, see, this you have to divide it by 9810 to get the proper G value. So this is, how much is this value? So this value is nearly 96. So this much it is. So this you have to divide it by 9810 to get the G value. Okay. Okay. So as I'm telling, like, my materials are the assumed materials. So with that I'm getting some results which are maybe like somewhat different from your expectations. So, and if you are putting a proper, if you are putting a different material, of course it will be a different material in your case. So you have to use those parameters if you want to match the results with your physical entities. Otherwise it will be different. Okay. So these are some of the things which I wanted to share with you. So as you see in the explicit, explicit will not limit you to represent any physics for that matter. Here there is a lot of options which are available to represent any kind of physics. So it is, you're no more in a linear or implicit nonlinear domain where you have to think of the constraints, or you have to think of some assumptions to idealize your representation. Here it is not required that. Like here everything can be represented. There are a lot of options in terms of contact, connections, the loading. So everything can be represented in a more physical way. So I hope this was useful for you, and I hope like you will try this, and some days when you work with the radios, I hope we'll interact. Okay. So we are getting many questions, but so if I open the question line, there will be like too much of crowd. There are many people. So you write your questions, and as I mentioned, we will surely reply to your questions. Okay. So fine. Thank you. Okay, so some information. Sorry, I missed out to tell this information. there were some slides which were my last slides. If you felt like okay, something was very fast, and of course you will be having access of this recording also, but apart from that, if you want to do something something more, something extra, then so regarding these chapters, in the YouTube you will find the videos, like maybe how to create materials, how to create different connections. Here I almost created, here I almost didn't create any connections, but you will have a separate video on how to create all these connections, how to create these contacts. Here again, we didn't create any contact. We created only type 2 contact, but we didn't create any surface contact. So in this whole bunch of videos, what I have done is I have just taken a meshed model, and on that meshed model, I have updated the materials, properties, connections, loads and boundary conditions, contact, output request, everything, and then finally I'll make it as a runnable model. So this is a full car model, and the video is for all the videos put together, maybe around, it is a nearly some 3 hours video. So you can have a look on this. So this will give you more insight about using hyper mesh for radios. So again, I'm telling this will only help you in the getting conversant with the pre-processing. So this is not on the solver front, but this will surely help you as you are starting afresh. These videos will help you. And for questions, I request you to write to, oh, just a minute. Okay, so I have the ID here. Okay, so please write your questions to this email ID so that I can take them up and reply you. Okay, so I'll be looking forward for your questions in this email ID. Fine then. So thanks a lot. So let's do the design more faster, stronger and lighter. So that is the vision of our time. Thank you very much.